This is a problem from mechanics that I know I've had you do a couple of times, and I want to review it now and have you study it again, both to refresh your knowledge of mechanics, but also because this particular um, physics concept, physics idea, physics principle is going to pop up very soon in our study of E&M, where in order to calculate the work done, we're going to need to take the integral of a force. So here we have a nonlinear spring, and so what that means is we're assuming that the force has this form, and we want to know what quantities we could graph in order to yield a straight line with a slope a. So if we graph f on the y-axis versus x squared on the horizontal axis, the slope would equal capital A. So what we can actually do then is just go ahead and fill in the table that way. So using that as a guide, what I'm going to do is I'm going to calculate the x squared in decimal form, and then I'm going to go ahead and actually write it in scientific notation, and you'll see why in a second. So this is 0.0025. So I'll write that as 2.5 times 10 10 to the negative 3. Continuing here, this 0.1 squared is 0.10, which is 10.0 times 10 cubed. I could write this as 2.50, I suppose. And then 0.15 squared is going to give us 0.0225, which is going to be 22.5 times 10 to the negative 3. And then we'll take 0.2 squared, and that's going to give us 0.04, which is going to be 40.0 times 10 to the negative 3. Lastly, when we take 0.25 squared, that's going to give us 62.5 times 10 to the negative 3. So here's why I want to do that. On my graph here, I'm just going to make a little note that this is times 10 to the negative cubed. And then here, this will just be straight from 0 to about 100. Let's just count this off. So let's see, 20, 40, 60, 80, 100. Great. So 20, 40, 60, 80, 100. And again, that's the force in newtons. And here we're plotting the position squared times 10 to the negative 3 in meters squared. So we need to go from 0 to about 62.5. That's the range. So let's just count squares here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 5 is 60. So why don't I count off by 5? So this will be 10, 20, 30, 40, 50, 60, and then this would be 65 times 10 to the negative 3. And that allows us a nice range of x values. So at 2.5, I have a force of 4 newtons. So this is about the 2.5 mark, and 4 newtons would be about right there. At 10, my force is 17. So right about there. At 22, it looks like my force is 38. So 22.5, so 10, 22.5. It looks like I had a force of about, 38? Okay. So 22.5 and about 38 right there. Next, at 40 times 10 to the negative 3, we have a force value of 68. So right about there. And then lastly, at 62.5, we're at about 106. So right about there. And now we can go ahead and draw a line and use that to calculate a slope that we can use to get A. So again, I'm kind of approximating here. So I'm going to pick 2 points now. I've got the graph plotted, so I've done A, B, and C, and now let's calculate A from the slope, which we can do directly in this particular case. So let's pick 2 values. I like this value right here. That's 60 times 10 to the negative 3, comma 100. And we can compare that to, again, we're kind of approximating here. Let me try to find a value that at least approximately makes it. Roughly speaking, it's not quite on the square, but I'll go with 10 times 10 to the negative 3, comma 20. So that's going to be 80 over 50 times 10 to the negative 3 when I get my rise over run. So let's just do that right now. So 80 divided by 0.05. And that's getting me about 1,600. And the units would be newtons per meter squared. Awesome. Now it says calculate the work done by the cart in compressing the spring 0.10 from equilibrium length. I think one thing that sort of got me here is this is not a Hooke's Law spring, and I saw a lot of people write 1/2 kx squared. We've done this problem repeatedly, so I don't know what it's going to take. I think what it's going to take is me just forcing you to do this problem repeatedly. So it's not 1/2 kx squared. You've got a force here. So let's be really careful. The work here is going to be the integral of f of x dx from 0 to 0.1. And in this case, that's going to be 1,600 x squared dx integrated from 0 to 0.1. So that's going to give us 1,600 x cubed over 3 from 0 to 0.1. When I actually calculate that out, I'm getting about 0.53 joules of work. Now I can use that to get the speed because I can use work kinetic energy theorem. So I know that work is the change in kinetic energy. So that means 0.53 equals, and that's going to be negative work since it slows us down, 1/2 times 0.5, which is the mass, times 0 squared minus 1/2 times 0.5 times v squared. When we actually go ahead and solve for v, we're going to get a speed of about 1.46 meters per second. All right, so that is question number 10 on our practice test bank.